is part 4. It's chapters 10, 11, and 12. And it's all about analytic geometry. And this is a very important tool that we use in the calculus. It's a combination of geometry and algebra, as opposed to the propositional geometry that Euclid gave us, a couple thousand years ago. So we're going to look at this whole idea of analytic geometry, combining tools to analyze eccentric functions. That's what the whole course is about. Pre-calculus is all about functions. Okay, so we've introduced a lot of tools along the way, and we're going to actually apply them now to a lot of things later on, especially in chapter 11 when we start to look at the graphical analysis of all the functions. We introduced all the functions we're going to be talking about already, and then we introduced some tools on how to work with them. We're going to introduce some additional tools today, and then we're going to start applying those tools to analyze functions in a geometric way. We'll visualize them and try and talk about what's happening with them, how they're changed, their weights have changed. That'll get us ready and primed for a course in calculus, which deals essentially with all these rates of change. Okay, so let's begin this section over here, and this is 10.1. And here are some, basic tools. For analytic geometry. These are more the geometric tools rather than the strict algebraic tools, although they look algebraic, but they provide us with geometrical insight. The first tool we're going to introduce is how do I find a distance between 2 points? Points on a graph. Okay, so let's take a look at that. So I have my Cartesian coordinate system here, and I have one point here and another point there, and I'd like to find the distance that spans those 2 points. Okay, let's give them coordinates. I say this has coordinates. This would be my x1, so this is, call that point 1, it doesn't matter. And here's my point, y coordinate of point 1, the x coordinate of point 2, and the y coordinate of point 2. And I would like to find the length of that distance. Well, what do? Go back to our old staple, the Pythagorean identity, Pythagorean theorem. Meaning I will construct, if you will, a right triangle here. I'll find this distance, that distance, and we know that this distance squared plus that distance squared is equal to d squared. Okay, so let's find what each of those are. Well, if I bring this down here, this is my x2, there's my x1, this is my y2, and here's my y1. So what is this distance here? Well, this distance right over here is nothing more than x2 minus x1. So that's the length of that red line there is just x2 subtracting x1. And that'll give me the length of that right there. This distance over here, everyone can plainly see, is just y2 minus y1. And that's the distance for that right here. So this distance right here is my, we'll put it at, we'll have my y1 minus y2. So it's this height minus that height. This distance minus that distance. Okay, now we know those values, so I can use the Pythagorean theorem. And have my distance squared is this length squared, so it's x2 minus x1 quantity squared, plus distance over here, y1 minus y2 quantity squared. And if I want to find that distance, well, I can take the square root. Now, ordinarily, when you take a square root, you can look at the plus or minus, but distances are always positive. So we do not need to consider the negative because we're only dealing with positive distances. So I end up with the distance is the positive square root of this. And I'm going to make another simple observation over here. Notice I have, they look similar, but the 2 comes first and then 1 comes first. But if I look at this, I notice that y1 minus y2 squared is equivalent to y2 minus y1 squared. Well, why is that? Well, I could factor out a negative inside of that. Right? And just factor a negative out of these two, that one minus that one. And then I can square that, so that's a negative 1 squared times by y2 minus y1 squared. Why do I do that? Typically, we write a formula this way, just so it's a little more consistent. x2 minus x1 squared plus, and I flip them over here, y2 minus y1 squared. And that's what we do. That is our distance formula. And we can find the distance between any 2 arbitrary points in the xy plane. Here's our distance formula. So d, again, I'm only taking the positive value. The change in the x squared plus the change in the y squared, square rooted. Okay, let's just do a couple of applications of it. Example. We'll start with a simple one over here. What is the distance between the 2 points? Say, -3, 2, and 5, comma, -4. So we have those 2 points. I could draw the picture of them and see what it is, but I don't have to. Now, the nice thing about this, we don't care what's point 1 and point 2, because when I square everything, it all becomes positive, and so I don't care. I usually just call the first one point 1 and then the second one point 2. Now again, it does not matter how we choose to label this, but I'll call this point 1 and this point 2. It's not going to matter, because the distance from point 1 to point 2 is the same as the distance from point 2 to point 1. Doesn't matter. Okay, so that means this is my x1, y1, x2, y2. Plug that in, and I get my distance then. It's the square root of, so I have my x2 minus x1, so that's 5 subtracting a -3 quantity squared, plus my y2 minus y1, which is -4 subtracting 2 quantity squared. And squaring everything out, I have my distance is equal to 5 plus 3 is 8, so I get the square root of 8 squared, which is 64, plus -4 plus 2 is 6, so I get 36. Positive, because I'm squaring it, I get a -6 squared gives me positive 36. So the distance here happens to be, I just arbitrarily made it all work out. I guess that's 3, 4, 5 are going there. Square root of 100, which is exactly equal to 10. Oftentimes we don't get exact answers. And what we typically like to do is we'll leave it with the square root symbol. Okay, this is a concrete example. Well, in the calculus, it's going to be a little more abstract. For example, you might be asked to find the distance in this more abstract type of example. So let's give you these 2 points. Let's give the point x comma f of x, and another point x plus h comma f of x plus h. So you need to be understanding of this formula in this more abstract setting. This is a more concrete, finding a fixed number distance, but you need to get up to this level of abstraction to be able to handle the calculus. Again, I'll call that point 1 and that point 2. Now I'm not going to get an exact answer. I'm going to get it in terms of the function f of x. It's what I have. If you draw that as a picture over here, what am I looking at? So here's a picture over here. And this is, say, some function. So y equal to f of x. So I'm looking at here x, and I'm looking at over here that x plus h. So that distance here is just h. This is my f of x, and there's my f of x plus h. So I'm actually looking for this arbitrary straight line distance between those points on any generic graph. F of x can be any function. Okay, let's plug that in and see what we get then. Well, in fact, why don't you try that? Plug this in and see what you get. Work the algebra. I can do it, but I want to see if you can do that. We got the formula. See if you can identify. Here's your x1, y1, x2, y2. Plug that in and see what comes out. Give you a minute to do that. This is a level of computations you should be striving for. That this doesn't seem to be so foreign to you. That'll make the calculus all the more easy. Multiply everything out and see if you can get this. And if you can't, we'll see it. So one way to represent that distance d is as follows. Okay, so if you multiply everything out, you get something that looks like that, or you can change the order. You can change the order of those, but that's just one way of writing it. Look complicated. We'll get expressions that look fairly complex in the calculus, so get used to it. And get used to it looking at abstraction. Okay, does anyone want to see how I, got that for my distance? We can kind of see how to do that by plugging in. Okay, so I'm plugging into my distance formula. And it's the square root of, let's take this over here. I'll take my x2 minus x1 quantity squared. So take my x2, which is x plus h, minus x1, which is x, and I square that. Plus over here, then I take my y2, which is f of x plus h, minus my y1, which is f of x, quantity squared. Okay, well, over here I can see readily the x's cancel out. X minus x, this just gives me h squared. So the distance here is h squared. Plus, well, I can multiply this out. Remember, on the side we have, so we have f x plus h minus f of x times f of x plus h minus f of x. So I have this times that. That's going to give me f of x plus h quantity squared. So this times that. And then I'm going to multiply this times that, and as well as this times that. Both of them are going to give me negative f of x plus h times f of x, and I'm going to have two of them. It gives you minus 2 of those f of x plus h's times f of x. And then the last, the negative f of x times the negative f of x gives me positive f of x squared. And that's it. So that's the type of